And you will be talking about gravitational waves from charge-carrying domain balls.
Okay, thank you very much for the introduction. Okay, I'm Yu Hamada. I'm a postdoc from DESY. And today I'd like to talk about my recent paper, which actually appeared on this Monday. So you can, so please look at the paper if you are interested. So, okay, so this is based on a collaboration with Anish Ghoshal. And yeah, we talk about some, gravitational wave from a domain wall, but actually the domain wall is, different from the conventional domain wall. It's actually can carry some internal degrees of freedom, like a domain wall can capture some, particles in the bulk. Then this gives some, non-trivial gravitational wave spectrum. Okay, let me start. So, as is already mentioned in the many talks in this workshop, domain was a very nice, exciting object which appeared in the many BSM models. So domain was one of the topological defects, and it's a kind of a remnant of some spontaneous breaking of discrete symmetry. For instance, if we consider some scalar field phi, and then if this has some scalar potential like this double wave type potential, which has a Z2 symmetry. And if this scalar field phi takes a wave, like a plus V or minus V, then this global Z2 symmetry is spontaneously broken. But in this case, the domain wall appears because in principle, the different Hubble patches can take different waves. Like let's say this domain has a plus wave, positive wave. On the other hand, this different domain takes a minus wave. Then in between, there must be some boundary connecting these two different waves. This is called a domain wall. And because domain wall has some finite energy, finite tension, so it can dominate the energy density, total energy density of the universe, because its energy density is proportional to the scale factor -2, which is much, much slower than that of the radiation energy density. So at some point, this can overcome the radiation energy density, then this gives, overclosure or, the dominating energy density. So clearly, this is inconsistent with the current cosmological observations, like CMB or BBN and so on. So in that sense, domain wall is a kind of a dangerous object, and they must decay at some point by the current universe. And there are several ways to destroy domain walls, but one of the way is to introduce a bias energy in the scale potential like this. So here, I introduce some bias energy denoted by delta V, which lifts up one of the waves, like this figure. And this, so clearly this explicitly breaks the Z2 symmetry in the potential. And thanks to this bias energy, let's say the minus domain does not change, but the plus domain gets some additional energy compared to this minus domain, like this, this energy density given by this energy density. That means, so energetically, this minus domain is favored. Then this plus domain is not favored. That means, so minus domain can push the domain wall to shrink. So that means effectively this bias energy delta V gives some pressure to the domain wall. Then this tends to shrink. So this can be shown in this picture. So let's say that the minus V is energetically favored, but this plus V feels some bias energy. Then this minus domain pushes the domain wall to shrink, like this figure. And in the end, this domain wall, this domain plus domain disappeared. That means the domain wall also disappears. And this happens at some cosmological time, which is given by this quantity. Here, sigma is the domain wall tension, and the delta V is a bias energy. And this motion is actually very nice because this motion can radiate the gravitational wave, which is clearly shown by this quadruple formula. Here, this is a radiation gravitational wave energy radiated per time is given by some Newton constant times some some time derivatives of the quadrupole square. Here, so this capital Q is a quadrupole moment of the energy density, and this is given by roughly given by this quantity. Yes, sigma is again the domain wall tension, and R is some domain wall size, which is typically given by the Hubble radius or Hubble size at that time. At that size when the domain networks decays. So this is just a simple approximation, but actually this is confirmed by the a lot of numerical simulations. So so here, sorry, they are a little bit old simulations. So there, of course, there are a lot of newer numerical simulations. But yeah. So for example, in these papers, they simulated some collapse of the domain wall network starting from some some randomly distributed domain wall. Then as you can see, they can decay by the barrier energy. And then also they calculated the gravitational wave spectrum like this. Then we can see some clear peak radiated from the domain wall networks. And based on these calculations, we can compare the gravitational wave spectrum coming from the domain wall network and some future gravitational wave observatories, like this figure. So then we can see that in the near future we might observe some gravitational wave from domain wall by these gravitational wave observatories. Or we could say that the PTA signal can be if we already observed the domain wall the gravitational wave from the domain wall by interpreting the PTA signals as a that domain wall network. But anyway, so in this sense, domain wall is a very exciting object. Then we could see in principle by the these gravitational wave observatories. But actually, this is just a standard story about the domain wall network. So in the following, I will explain that when we take into account some particles that trapped on the domain wall, that captured on the domain wall, then the gravitational wave spectrum coming from the domain wall might change drastically. So before going to the detail, I just show how the gravitational wave spectrum changes by this effect. So this is just a conventional spectrum, as I showed in the previous page, coming from the collapsing domain wall network. But when we take into account the particles trapped on the domain wall, actually we have an additional peak, secondary peak in the gravitational wave spectrum. This is clearly distinct from the conventional gravitational wave spectrum. So this is something like mountains. So the gravitational wave spectrum can be much more non-trivial than expected before. So it should be like a two peaks mountain instead of just a simple one peak spectrum. Okay, in the next session, I will explain what is this domain wall. So that is actually called current carrying or charge carrying domain wall. And by using that, I will show the gravitational wave spectrum radiated from this kind of domain wall. Before explaining what is the current carrying domain wall, I just show I just review the usual conventional domain wall. Here, again, let's assume that let's consider the real scalar phi, which has some Z2 symmetry in the Lagrangian like this. Again, the scalar potential is something like this one. And again, this takes waves, then this Z2 symmetry is spontaneously broken into nothing. And by solving the static equation of the by solving the static equation motion, we can get like a domain wall solution. So this is analytically given by some tangent hyperbolic function. So this means that the domain wall solution is given by something like this profile. That means at phi infinity in the negative side, this is almost constant, and also in the positive side, this is also constant. But around x equals 0, there's some jump connecting these two different waves. So this has some finite energy, and this is regarded as a domain wall locating at x equals 0. Okay, then let's consider some Dirac fermion, which is coupled to the domain wall, like this, given by this Lagrangian. So here, this is just Dirac equation, and this is just a Yukawa interaction. And then, so we have to solve the Dirac equation, but let's ignore the YZT dependence, which means that because the domain wall is now domain wall is located on the x equals 0. That means the y and z directions are homogeneous. So let's forget about the YZ directions. And also, let's assume that this solution is static. Then Dirac equation is simplified into this expression. And this is easily solved by, easily solved. And then we can get some analytic expression for the solution, like this one, denoted by psi 0. So this is showing that in the positive side, in the positive infinity of x, then this phi dw, which is a domain solution, is almost constant, plus constant. That means this exponential function is exponential minus x times some plus constant, which means that this is going like a, decaying like exponentially in the positive side. On the other hand, in the negative side, this phi dw becomes a negative constant. That means we have an exponential of minus times the minus x, or negative x times the negative constant. That means it's also going like a exponential decay in the negative side. So this means that this solution of Dirac equation is localized around the domain wall, like this profile, like this plot. And actually, in the YZ direction, which is a longitudinal direction to the domain wall, this localized solution behaves as a massless particle because it can propagate along the domain wall with the speed of light. That means we have some massless particle which is, completely confined on the domain wall. So if this particle if this field psi has any charge, which can be either global or local, or this can be dark charge or whatever you want, then this domain will carry some charge or current because some massless particle can flow on the domain wall, and this carries some current or charge. That means the domain wall itself can carry some carries charge or current. So in other words, the domain wall can be regarded as some superconducting object, superconducting membrane, because the current can flow on the domain wall without any dissipations. So yeah, this is interesting phenomenon. So yes, but you might think this kind of domain wall is quite special. This is a weird object, but it is not the case. So actually, in many BSM models, this kind of charge carrying or current carrying domain walls can appear. For instance, if you consider some some extended some extension of the standard model in the visible sector, like okay, let's say I would say the simplest example is a 2 Higgs orbit model with some global Z2 symmetry in the Higgs potential. Then this can have a charge carrying domain wall or charge carrying domain wall. Also, you can consider some singlet extension of the 2 Higgs orbit model, or also the S10 GATT also has some this kind of domain wall. I mean, the S10 GATT also predicts the existence of the charge carrying domain wall. And also in the dark sector, so if you consider some fancy fancy models in the dark sector, then this sometimes this can also predict the charge carrying domain wall, like a spontaneous CP validating model. Violation, or a model with a left-right symmetry, or twin Higgs orbit model, and so on. So in that sense, I would say the current or charge carrying domain wall is quite common in many BSM models. Okay, then so far I just mentioned on the planar domain wall, which is extending in the YZ direction infinitely. Well, let's make it curved. I mean, let's form a sphere made of this domain wall. So this is a two-dimensional sphere made of this domain wall, which is embedded in the 3+1 dimensions. Again, we can have almost the same argument. So again, by solving the Dirac equation, some massless particle is localized along this domain wall sphere. So this is like confined in this two-dimensional curved surface. So again, so this domain of sphere can carry a charge or current due to this confined particle. Okay, this is this is the explanation about the explanation about the charge carrying domain wall. Then in the next section, I will show how can the gravitational spectrum be modified by this charge carrying domain wall. Sorry. So again, this is the same figure as that I showed it previously. So this is just a reminding you of the bias energy for the domain wall network. Again, so we have some bias energy in the potential. Then the domain network can collapse due to the bias because this bias gives some pressure to the domain wall again. Again, this is almost the same figure. Again, so due to bias term, this domain wall will collapse. I mean, will shrink due to this pressure. But now, what is different is the domain wall can capture some particles. I mean, capture and store us on the domain wall itself. For instance, these blue dots, blue points, are denoting some free particles in the plasma in the universe. But when the domain will shrink, so the domain will can touch these particles in the plasma, then they can capture and store us on the domain wall, like these red points. Red points means some captured particle on the domain wall. So then, as it shrinks, the domain wall can capture a lot of particles. And the number of the trapped particles is roughly given by this equation. Here, this n psi is just a number density of the particles in the bulk. And also this is, this is roughly speaking, this is just a volume that this domain wall sweeps. So here, R0 is a Hubble size. This is like a, initial size of this initial radius of the domain wall, which is given by the Hubble radius. And this is, the size of the domain wall. So this is like a, when it shrinks, some volume is swept by the domain wall, then this can, captured some particles given by this expression. Due to this capture process, some non-trivial things happens. So let's assume that the domain wall becomes a sphere for simplicity as it shrinks, whose radius is given by capital R. And each trapped particle on the domain wall has some energy given by this expression. Here, this J denotes some angular momentum of the trapped particles. So this is, analogous to some hydrogen quantum mechanics. If you consider some electrons trapped around the hydrogen atom, then this trapped electron is labeled by the orbital angular momentum, right? Then if when this this electron has an angular momentum J, then this has some energy given by this something like this expression. Then let's consider the energy of this domain sphere here, which is given by this equation. Here, the first term is simply given by the domain tension, which is proportional to area of this sphere, and the second term is given by the some bias energy because the inside the domain sphere, this has some bias energy compared to the outside. So that means this is proportional to the volume of this sphere. I mean, inside of the sphere. And the third term comes from this trapped particle. So you have to take summation of the energy over all trapped particles on the domain wall. So that means you have to take summation of this energy. Then this gives this expression. Here, you can see that this is proportional to 1 over R. That means this is a kind of repulsive force coming from trapped particles. So this means that the energy of this object has this R dependence, this R dependence. So for large R, this is just going up, but for small r, we have a 1 over r term. That means this is going up again. This means we have some minimum of this energy at which this domain or sphere is stabilized at finite r. So after the stabilize, this behaves as some stable let's say metastable object, which we call spheron. So yeah, this is a little bit confusing with spheron. This is completely object, but okay. So let's call this a spheron because it's a kind of sphere object. Okay. Well, actually, this is a kind of too optimistic explanation, too optimistic case. So we have some additional two conditions to have enough particles on the domain wall. The first condition is that so naively, when the domain will capture the particles, then such a particle has a positive energy charge and a negative energy charge, whose whose number should be the same, roughly speaking. But in such a case, that means the net total charge, net total trapped charge is 0. That means we have some pair annihilation on the domain wall. So, particle of psi and antiparticle of psi on the domain wall can annihilate due to the pair annihilation. That means this decreases, this reduces the number of the trapped particles on the domain wall. So that means in order to have enough, in order to have a large number of the particles, we need some charge asymmetry in the domain wall. So in the following, I just simply assume that the trapped particle is a maximally asymmetric. That means, let's say that all of the particles is just a positively charged, let's say. Then that means the trapped net charge on the domain wall is simply given by the number of the trapped particles. This is just an assumption, but this depends on the cosmological scenario and also the BSM models. So here I don't want to specify the models. So I just simply assume that there's such a maximal asymmetry. And the second condition is that in order to be captured, the momentum of the particles in the bulk should be less than its mass. So this is clearly understood from the Dirac equation. So as I said, the particles can be trapped on the domain wall because, by solving the Dirac equation. And if you look at the Dirac equation, you can see that, this term is roughly speaking, this term is corresponding to the mass of the particle. And this, of course, corresponds to the momentum. If momentum is much, much higher, much, much larger than its mass, then effectively this does not feel any potential, any coupling to the scalar field. That means momentum should. That means the particles cannot be trapped on the domain wall. This just passes through the domain wall. So in order to be trapped, in order to be captured, this momentum should be less than the mass of the particle. That means the psi particle should be non-relativistic in the bulk. So naively, these two conditions looks like, to satisfy these two conditions, maybe the one of the nice example of the BSM model is something like asymmetric dark matter, right? Because if we need some charge asymmetry for the particle, and also this should be non-relativistic. So this is like dark matter. So that means maybe the asymmetric dark matter model is a maybe good example to realize this situation. But anyway, I don't want to specify any models. So just let me proceed without the concrete models. Okay, so this metastable object, which we call spheron, is actually not absolutely stable because this can decay by some quantum effects. For instance, the first process is called fission, which is just a decompose. So let's say this is just a decomposition of this object. So based on some non-perturbative process, this spheron can be decomposed into, let's say, two parts. And here the total charge is conserved, right? So this initial charge is Q, but this is going to the half of the Q, into two smaller spherons with a charge is whose charge is 1 over Q over 2. So the total charge is conserved, but actually this this decreases its energy. So this is possible, kinematically possible. And the second process is simply just a decay of the charge carrying particles on the domain wall. So here, this trapped particle psi could decay into lighter particle, like standard model particles. Of course, this also depends on models, but in principle, this can happen. And so this is more like a perturbative decay because this is just a decay of the charged particle. So this is simple, simple decay process of the particles. In any case, so spherons can lose their charge Q by these quantum effects, quantum processes. That means after losing their charge, then this can shrink again because the energy relation is given by this curve. And then if they lose their charge, then this is shifted to this like orange line. That means the minimum of the radius is shifted to left. That means the spheron can shrink when they lose their energy. Sorry, but when they shrink, actually they can radiate a gravitational wave because this process is not spherically symmetric anymore. Which fermion? Trapped fermion? Same field. Yes. Okay, so if you mean the if the same particle exists in the bulk, then this can scatter the spherons, right? Okay. Yeah, I think this is possible. Yes, this should be possible, but I didn't consider actually. Yeah. Well, yeah. And maybe this can, deform the spheron with some rate. Yeah. Yes. That could be possible. Yes, I see. Okay, yeah, let me consider it later. Yeah. But I think so. Anyway, this particle is non-relatively thick in the bulk, so that means its rate should be small, I guess. Yeah. Okay, and so as clearly seen, this process is not spherically symmetric anymore. That means if this process happens, then this is gonna randomly oscillating, and then this can radiate a gravitational wave. And as this shrinks again, this is stabilized with a smaller R at this point again. So that means this becomes like a smaller spheron. But again, this can lose their energy by these processes. So that means loses the energy and becomes smaller radiating gravitational wave and stabilize. And again, loses their charge by this quantum effect and so on. So this is like a sequence. This happens continuously until they disappear completely. So this gravitational wave, energy can be calculated by using the quadruple formula. So here, the typical frequency of the gravitational wave is given by the 1 over R spheron. This is the size of the spheron. And the quadruple formula is given by this equation. Here, this MdW is just the energy of the spheron, and this is again the size of the spheron. So by using this, we can roughly estimate the energy fraction of the energy density of the gravitational wave. So this is given by this equation. So here, this term corresponds to this part corresponds to just a quadruple formula, and then more non-trivial points is that these two factors. So this factor corresponds to the time scale of the radiation. So simply, this is given by some decay process, decay lifetime of this process. But actually, the radiated energy from the spheron must not exceed the total energy of the spheron itself. Otherwise, the energy conservation is broken down. So that means we need some cutoff for the radiation time scale. And this factor corresponds to the number density of the spheron at decay. So this means, when the spheron is produced, this number density is given by the 1 over Hubble size. When the domain wave network decays, domain wave network collapses, and this is of course diluted by some scale factor because effectively it behaves like a matter object. And we can rewrite this gravitational wave energy density in terms of these parameters of the domain walls. Here, sigma is again the tension of the domain wall, and the T decay means the temperature of the universe at which when this spheron decays. And this capital Y is the yield of the number density of the trapped particles in the bulk, which is divided by the number density of the photons. So clearly, you can see that this has a very strange parameter dependence compared to the conventional domain wave network collapse. So in the conventional domain wave network collapse, its energy density is given by this parameter, these expressions. But comparing them, so you can see that this parameter dependence is very different from the conventional domain wave. So this is interesting point. And then it's a gravitational wave spectrum is given by something like this peak. So here is the position of the peak corresponds to the size of the spheron and some redshift factor, and then this IR behavior is almost determined by the causality argument. So this should be the F cubic behavior. On the other hand, this UV behavior corresponds to the UV behavior is taken to be F to the minus 1. So actually, this is just an assumption by hand. So this, this is simply taken to be the same as the conventional domain network. So this could be different, but at this stage, we just simply assume this behavior for the UV regime. Then, as I mentioned in the introduction, so we have a superposition of the both gravitational wave from the conventional domain network and from Subhendra, which is new one. That means we have a conventional peak coming from the conventional domain network collapse, and also we have another peak coming from the Subhendra decay. That means by taking superposition, the spectrum should be the two peak spectrum, like one peak coming from the one peak corresponds to the size of the domain network. On the other hand, this second peak corresponds to the size of the Subhendra. Yeah, second peak appears. So by calculating the, this is showing the plot for the gravitational wave spectrum coming from Subhendra. So we can see that. So we see, we have two peaks. So this left peak corresponds to the conventional domain network, but this right peaks, like two different lines correspond to the two different benchmark parameters. For instance, if you look at the blue line, then this right peak corresponds to the Subhendra, and also this peak in the orange line also corresponds to the Subhendra. So they have a different position. Their positions are different due to the benchmark parameters are different. And this is the plot for the SNR. So here we calculated the SNR for the conventional domain network and the total, let's say total gravitational spectrum, including the conventional domain network and the Subhendra. Here the dashed line corresponds to the conventional domain network, but this solid line corresponds to the the summation of the conventional one and the Subhendra. So clearly we can see that thanks to the Subhendra, the SNR is significantly improved. And this is a parameter space in which the SNR exceeds 10. So here, horizontal axis is a domain rotation, and the vertical axis is a bias energy. Then these dashed lines correspond to the conventional domain wall without Subhendra. But if you take into account the Subhendra, then we can have a wider range for the parameter space in which the SNR exceeds 10. For instance, okay, let's say, for instance, this region, if you don't take into account Subhendra, then in this region, the SNR is smaller than 10 when you consider only the domain network. But by considering the Subhendra, then this region can be this region can have a SNR larger than 10. That means the Subhendra helps a lot to detect the gravitational wave signal. And also this is a plot for the about the domain network interpretation for the PTA signal. Okay, so if we assume that the PTA signal, observed PTA signal, can be explained by some conventional domain network, then so it is possible by taking these parameters. Then due to the Subhendra, another peak from the Subhendra can appear in the range of the LISA. So this is very nice. So if you explain the PTA signal, then our scenario can predict additional peak in the LISA range. So this is a very nice point. Okay, let me summarize. So as I mentioned, the conventional collapsing domain network can radiate gravitational wave. But if we take into account some particles trapped on the domain wall, then a new metastable object, Subhendra, may survive, may exist and survive until they decay. And so this is, if you are familiar to the Volton, then this is like a domain wall version of the Voltons. So the Volton is like a cosmic string loop carrying some current or charge. Or if you are familiar to Q ball, then this is also this sphere is like a domain version or sphere version of the cue ball. So this is very so I would say this is like a hybrid of the cue ball and the photon. Okay, then decaying sphere can radiate gravitational wave, which gives some secondary peak in the gravitational wave spectrum. So this is so in the end, so the spectrum should be like a 2 peaks mountains, like this figure. Okay, that's it. Thank you very much.
Thanks you. Questions, Subin?
If you start with a planar object, you cannot form a sphere. You'll form a sphere with a puncture. And once you have a puncture, then both the domain wall tension as well as the charge on the ring would I would give you back a planar object, right?
Sorry, can I say again?
See, if you start with a plane, you cannot form a S2. You can form a S2 with a puncture. With a, right? Topologically, they are not the same thing. Now, if you have a puncture, then the tension of the sphere would, and also the charge on the ring, which will repel each other, will give you back a plane.
Sorry, you mean how to form this sphere?
Yeah, you cannot form a complete sphere. You can have a sphere with a hole.
Sphere with what?
Puncture. Topologically, these two are not the same thing, right?
Yeah, sure. But this completely plane object does not exist in our universe because everything should be every domain should be closed in principle. I mean, okay.
Well, you could start with have a sphere at the time of formation and then do all this. You don't need to start with the domain wall, no?
Well, okay. So in principle, the domain wall network consists of the large size, large closed domain wall, right? So that means every domain wall should be closed. Otherwise, the energy is like diverging. So that means when we start from the domain wall network, everything is already closed. Then by some random motion or by some reconnection of the domain walls, then this can sorry, no. When the network collapses, then this or this closed domain wall tends to shrink. Then this becomes like this sphere. Yeah. Yeah, sorry, yeah.
Other questions?
So I was just trying to understand why is the secondary peak to the right? I mean, and what is the relation between the T annihilation and T decay?
Well, okay, one reason is that, so basically the sphere, okay, so there are two factors. One is the, what determines the position of the peak is the sphere size and redshift factor. And typically the sphere size is smaller than the Hubble size. That means this becomes like a, more UV. And also the sphere decays at later stage than the domain wall network. That means we have a mild redshift factor. That means, yeah, due to this, this becomes right.
Other questions, comments?
Analytic, sorry?
Speak loud.
Sorry.
Or take the mic.
You mean you want charge for this psi, right? Okay.
Right, so I was thinking if you can incorporate a U1 charge for this psi particles, can that help in the primordial magnetic field kind of scenarios?
Well, okay, that's a very good question. And actually, I've never considered that. Well, it could be possible, but actually, I'm not familiar to the magnetogenesis stuff. So, well, I'm not sure, but yeah, when they decay, well, yeah, in principle, when they decay, this can, they can produce some non-trivial, non-trivial profile of the non-trivial magnetic fields. But yeah, actually, I have no idea.
Any other questions? I had a comment and a question.
Yes.
So the comment is that I was very glad to see this doubly peaked gravitational wave spectrum, similar to what I was talking about in my talk as well. It's something very interesting, and of course, it is also interesting to see whether you can, disentangle the origin of these doubly peaked spectrum, which is arising from, a scenario like this, because these two peaks are very clearly separated in the frequency domain. All right. And my question was that if you go to one of your second last or last slide, you're essentially plotting this spectrum for two different values of y here. Yes. And y essentially is this fraction of fermions to the, right? If I understood correctly. What is y? Y is the fraction.
Oh, y is
the number density of fermions.
Yes, yes,
correct?
Yeah.
So I can understand that if you have a larger number density of fermions, you would expect a larger amplitude.
Yes.
But what exactly decides the peak? Why does the peak shift by 2 orders of magnitude or 3 orders?
Yes.
So what physics does decide the shift in the peak, second peak location?
That's a good question. So if we have a larger number density, then the trapped number of the particles is larger. I mean, the trapped, trapped charge of the particle is larger, becomes larger.
Okay.
Then the size of the solution becomes larger. That means this is more like a IR, IR, how do I say? Yeah, so because it contains more particles, then this means that the size becomes larger.
Okay.
And the size of the, the position of the peak corresponds to the size of this object. That means larger object becomes like, radiates the more IR gravitational wave. Like this.
So larger size means, okay, because you're shifting towards the smaller frequency.
Yes.
Large wavelength, yes. Okay, that makes sense. Okay.
Yes. And about the disentanglement, yeah, that's a very good question. Well, yeah, actually, maybe, I think it's difficult to disentangled, but yeah, if you, or, yes, yes, at this stage it's difficult. But actually, we did not calculate the gravitational wave spectrum. I mean, we did not calculate the detailed spectrum, detailed shape of the gravitational wave spectrum. So if we find this shape of the gravitational wave, this shape becomes more non-trivial, then we could disentangle. But at this stage, we don't know the detailed, detailed spectrum. So I think it's difficult to disentangle.
Okay, and one more last question is that, is there a limit on the value of y that you can push this peak towards left, or there is some constraint on the value of y?
Okay, that's a good point. So actually it depends on the models that if you consider these trapped particles as a dark matter, then of course the energy fraction of the dark matter is fixed. That means if you fix the mass of the particle, then this here. Sorry, no. This So if you regard this particle as a dark matter, then this energy density is given by the observed dark matter Ricks abundance. Then so this y should be well,
it's proportional to the number density of fermions. So
something like this. So if you fix some n psi, then we have a we have a fixed y. Yes. But if this is not dark matter, so if we consider this is just a just long-lived particle, and then this can decay at some point, then there's no constraint on y, so you can freely choose. But yeah.
Any other questions, comments? If not, you had something to add? No? If not, let's thank you and Deva Prasad, both of them, speakers of this session.